This is the part of the lecture where we are going to have some fun. So for those of you who are watching this online, we will do it twice. So tomorrow we will be staying more on slides, and just today we'll be doing it. I'll just try to get rid of this. Okay, my God. Almost managed. Okay. Help. So we are going to talk about a MIPS architecture. We are going to realize it today. So this is our goal today and tomorrow. And if you're already looking at the slides, you will more or less see that the same thing is repeating twice. It is repeating twice because today we are going to mostly do it on the blackboard. And tomorrow we are going to go over it once again, this time using the remainder of the slides, okay? I don't trust the slides, I don't trust myself, so both of them combined should work well. I was also warned to make 20% less jokes. Okay? 20. According to requests. Okay. That's it. Okay. So, what we will do today is to take a look at the MIPS processor. You're not supposed to compensate for my jokes. I'm supposed to not make them. Okay. We are going to talk about the microprocessor, and we will start designing this thing so that it can be implemented using Verilog and all the techniques and tricks we learned before. Now we are going to start by explaining it so that implementation is relatively easy. It's not that easy, but it's also not that hard. So this is what we call a single cycle processor. When you remember what we were talking about, the digital design things, we always said that, okay, we have somewhere that holds the state. This is the internal state of our processor or of our digital circuit. And then this is our present state, if you want. That one gets modified to a combinational logic and then ends up being stored at the next clock cycle. And so whatever we do within one clock cycle is actually done by the combinational logic. We start here, we process something, and we write it back. Now, what we will try to do today and tomorrow is to see a MIPS processor who does everything to interpret one instruction in one single cycle. This is not the smartest way to do it if you want to have high performance. It's also not the smartest way to do it due to many other practical reasons. However, it's much easier to understand what's happening. Once we know this, in the following week, next week, we will talk about making it better and more interesting. It will look very similar, so we won't need to understand much more what is happening. The basic operation we will already have understood. What will happen is that we will see how we can make the same thing go a bit faster or a bit more efficient. This is what we will do. On the other hand, we were talking about data path circuits where the data is coming out of here, gets modified over the combinational logic, and then gets, how shall I say, processed. And we said that in data paths, the data moves in this way, and then we have a bunch of control signals. So this is the way data goes. And then there are decisions being made at every step of the way to differentiate, am I adding, am I subtracting, am I doing this? And so there would be a control part that tells the data part how the data should be manipulated. And usually here, there would be a finite state machine sort of thing that determines what the control signals will be for every step of the way. And these things will usually also get some inputs from somewhere or from the present state and tell you what we are going to do. So this is what we will be doing in the end. Once we are finished with it, tomorrow, later in the afternoon, we will start discussing how fast this thing works, which, as you know, will boil down to when I start here at every clock cycle, how much time do I have to spend so that everything that one instruction tells us to do can be completed and we can update registers, memory, whatever. So this is going to be the question when we talk about the performance of the processors. I think it's super exciting. I hope you also find it exciting. So this is where we were. Once again, our abstraction thing. And last week and the week before, we talked about the architecture. The architecture defined us what the processor should be doing. And the architecture was already taking into account some physical realization issues, because we were saying that the RISC processors are made in a way so that they can be implemented more efficiently in hardware. So we made some compromises. We said, we don't want to have all kinds of instructions. We want to have a minimal set that can be very flexible, can do a number of things. But we want to make sure that these things that he does, he can do very well. And now, once we have the architecture, the microarchitecture is the part we are looking now, is how to turn that part, those instructions, those R types, J types, I types, into actual working circuits. What are the building blocks? How do we bring them together? And once again, the processor will have the data path, which is the one that manipulates the data, reads it from the registers, writes it back. And then we will have the control part, which tells the data path what to do every step of the way. Exciting adventure. Now, this is again probably a bit of repeat right now. This week, we will be talking about the single cycle implementation, the single cycle microarchitecture. In the book, if you follow the book, you will realize, by the way, that the slides actually closely mirror the book. Most of the figures are one-to-one verbatim from the book. This should help you follow it more closely. And in the book, there is a chapter after the single cycle architecture about the multi-cycle architecture. Now, this is in the book. We will not cover it. In the multi-cycle architecture, each instruction is broken up into smaller pieces. And the problem, or not the problem, the problem that the multi-cycle architecture tries to solve is, they realize that there is a number of expensive things, memories, adders, in the architecture, and they want to reuse them. So instead of, and they say, hey, if we break it down to multiple things, I can reuse the adder that I do for calculating the next address, I can do arithmetic calculation, etc., etc. It diverges a little bit from what we want to explain, and they are not so popular, so we are not going to cover this. Translation for you, no questions on multi-cycle architectures in exam. And after that, we have one version of the implementation that's much more like the architectures we built. We will realize that we will again do the same. If you look at the first line, it says exactly the same. Each instruction is broken up into a series of steps. But in this case, instead of using the architecture to do one thing in smaller pieces, we will allow multiple instructions at different levels to go in parallel. We will talk about it next week. That will be a fun thing to do. Now, what does our microprocessor do? The first thing to realize is that everything starts with a program that is stored somewhere in the memory. And we've been through this thing. We have a number of building blocks. Let me look at my cheating sheet if I'm doing things right. Probably not. Who cares? We have a number of building blocks, and one of the main building blocks we have is a memory, an instruction memory. We have where we store the instructions, we have where we store the data, and the memory is organized in 32-bit words. And every 32-bit word has an address. So you are pointing to somewhere into this memory where there is some ones and zeros at this address, and everything starts from this point. You read one instruction from the memory. So this is what we are doing. Now let me confuse you and go here. What do? I'll just write the same thing that's on the slide. So what do? We read one instruction. And reading one instruction is actually very simple. We just go to the memory where the instruction is stored and read out the binary value. And then we want to understand what it wants, decode what it wants. So we read out this seemingly random data from here, which is like whatever, 1, 1, 2, 2, 3, 4, 5, 6. It's a bunch of zeros and ones. And we know that by looking at it, it will decode into an R-type, a J-type, an I-type instruction. And once we know what it is, we can understand what that instruction wants from us. And most of the instructions will require some sort of operands, and find the operands. Some of them will be immediately available. So it could be an immediate, it could be a register, it could be from the memory. We have to understand where to find from them. And then we have to do what the operation tells us, what the instruction tells us to do. So perform the operation. Some of them are simple, like loading, storing. It could be, add, load, store, a number of them. If we produce a new result, if we are writing something, we have to write it to the location that he wants, he tells us, write back the result. And then go to the next instruction. When we talk about the single cycle architecture, in one single cycle, we are going to do all of this. First, read the instruction, look what it is, try to find the operands for that operation, fetch them, bring them, perform the operation, and write the result. Then we are done with this instruction. The clock cycle is over. We update. We go to the next address. We pick the next instruction in the memory. So the memory was pointing to here. It will point to the next location. We will pick the next instruction and continue and continue. We've already hopefully convinced you that these instructions, when we run them, should be able to do every kind of program. They look very primitive, like all these load stores, branch not equal to, but you hopefully were convinced that we can calculate anything we want to do. So what are the main pieces? We actually saw a lot of the pieces. We need a memory element. This is clear. We had this. What else do we have? We said that these memories, as nice as they are a little bit slow. So we have a second type of memory, which we call a register. We have 32 registers, each 32 bits. Okay, you'll find it from somewhere. What else? Well, we have one memory to store the program. This is here. And then we need one memory to store the data. Technically speaking, you could imagine that these are the same memories. Just for didactic purposes, just imagine that they are two different memories for this part of the lecture. The memory is large. If you remember, the addressable memory is large. So rather than one single memory, there are multiple smaller memories. And usually the data and the program are stored at very different locations. This also means that physically, they would be written in different parts of the memory. And in this case, let's just assume that we have two nicely separated 32-bit memories. If it's a lie, you can leave it. Is that okay? Don't tell us stories. I know, but, well, makes my life easy. And at some point, we need to perform some operations, and moving data back and forth doesn't seem to be doing much. And for the things that we want to do, we have something that we call ALU, the arithmetic logic unit, something that can do a number of operations. And we already saw this when we were going through combinational logic. I'll show you it once again. And then some bits and pieces. We will need a program counter, to tell us where to go and fetch the data. So there will be a program counter. It's just a register that holds a 32-bit value. It will tell us, where do I find the next instruction? Then we will need some sort of logic to decode instructions. And after I have, picked my one instruction, have done whatever it is supposed to do, I have to go to the next instruction. Let's not be lazy, say instruction here. How do I find the next instruction? Well, the program counter has to be manipulated while I am dealing with this instruction. I have to figure out what will be the next instruction. Now, normally, if there is nothing else, we will just jump to the next location in the memory, which is 4 addresses more. But sometimes when we have a branch, when we have a jump, we may want to jump to a different address than immediately the address that would have normally come. So we will see these things, and we are going to join everything together and make one great processor that can execute already most of the common instructions that we know. And we will manage it with a piece of chalk on a blackboard. So if we can do this in a piece of chalk on a blackboard, we can certainly do it also using Verilog and other things. I mean, how hard can Vivado be, right? So many years of computer science students complaining about Vivado, yet nobody goes and writes a new one. Okay? Maybe it's not that bad. Or maybe it's not that easy to write a better one. I heard challenge accepted from somewhere there. Okay, that's great. By the way, that finishes all the jokes. So, this slide we have already covered. So this is the basic RTL design that we are talking about. We have a data path that takes the data from somewhere. It moves from one register to another one. Control signals help make decisions in between, and the control signals depend on state and input. And once we are done, once we have done all these operations, it is ready to move on to the next state, the next instruction, and the rate at which we can do this tells us how fast we can execute one instruction. And if we can do 1 billion instructions per second, we are we are good. That means that I have to finish each instruction in a nanosecond. Now, if you fasten your seatbelts, let's try to get started and try to come up with our processor architecture. And of course, I made a mistake. This is the wrong way around. No problems. Let's get going. How do we do? Now, don't worry. I will not cover anything that's not on the slides. In fact, we will cover these things more or less 3 times. Okay, but for a little while, I'm going to go away from slides. Watching at home or in July, fast forward to the part where we're only on slides. Okay. Let's do this. Perfect. We have light. We can start. I have my cheat sheet. You don't, which is excellent. So let's first start with our memory. There is somewhere in our architecture, already mistake, a memory. This memory is clocked for writing, but it is actually combinational for reading. What happens here is we have an address, and this address can be 32 bits wide, tells us which data to read out. Now, an instruction memory, this guy, we will not be writing into this instruction memory. We will only be reading from it. Technically, you could argue that, hey, Frank, you could maybe self-modify the code, write it back. Let's not consider that for a moment, okay? Let's just assume this is a nice memory who contains the data that we want to read out. And the data is also 32 bits. And this is more or less it. It's a combinational logic block. We are not writing to it. So this is my instruction memory. And I promised that I would be drawing these in yellow, and I didn't. Let's do this. Okay. Now, remember that I was talking about that we need a program counter to tell us where to fetch the instructions, right? So we know it's this data. Who produces the address? Well, guess what? We will have a register that has 32 bits, and this is a program counter. And this register is going to hold the value that goes into the instruction memory. It is the address. It tells us where we will find the next instruction. Now, we will come and close it. So this is the present. This is the PC present, right? We will talk about what happens to the PC next in a while. Is that okay? Clock comes. Program counter says, go here. We fetch some data. Now, this data is a larger 32-bit value. It comes out, and what we are now going to do is we are trying to figure out, reading the one instruction, is this what we did? Program counter tells us where to go. We go here, and we read out from the memory. This takes some time. It doesn't happen instantaneously. So we read out from here. We have a 32-bit value. And this value, we know that we should interpret this as an instruction. And we know that we have a number of different instruction sets. We say, you know, we have R type, we have I type, we have J type, and we know how they break down. For example, how do I recognize an instruction is an R type instruction? You say, if this is 32 bits, I will take a look at the first 6 bits. So if they are all zeros, all 6 of them are zeros, I know that we are talking about an R-type instruction. And then we say, okay, there is 3 times 5 more bits. So this is 25 to 21. Then there is 20 to 16. And then there is 15 to 11. These will be the RS, RT, RD. My God. And then there is a shift amount that we never talked about. And then there is the function 5 to 0, 6 to 10. So what we get from here is this. And right now, let's start very, very simple. Let's say at this very moment, let us only concentrate on trying to implement this R-type function. Okay? Now, in parallel to the data, so this is the data path. This is the data path that I'm trying to draw. So the data will be moving from this way to the other way. There will be some control signals which will come here, which is below, in a part of the control cloud. And they will make decisions based on what is happening. So somewhere I have to realize that, hey, I am actually doing an R-type instruction. How do I know that I'm doing an R-type instruction? Well, I will check the bits 31 to 26. If all 6 of them are 0, I know that I'm doing an R-type instruction. Who's going to do the checking? We will come to that in a little while. It will happen down here. But once I know that I am dealing with that type of an instruction, I realize every R-type instruction needs 3 registers. 2 to operate on and 1 to write the result. And where do I find them? You say here, there will be a register file. Hello. Here. And the register file, if you want to be efficient, what we will do is we will say, you know what? We have three different, I'll just try to be consistent with this. I have two read ports, and this is the first address. How many registers did I have in total? 32. How many address bits do I need to select one of the 32? 5. So 2 to the 5 makes 32. So with a 5-bit address, I can pick one of those registers. And the register output, just making sure that is the read one, will be a 32-bit value. This is the content of register that corresponds to this first address. Now the second one is similar. This will be the address 2. It will be again 5 bits. And this output will be read 2. Again 32-bit. What else do we have? Well, we are going to have a third address. We are not talking about it right now. And we are also going to have a write data that we need to write things back to. And certainly this guy is at some point also going to have a clock or something like that. Now, I know that, so this is another 5 bits. And this will be 32. Now, I know that 2 of my operands are coming, I mean, part of this 32 bits, it contains 32 values, and I know that this guy is the first address that goes here. So this wire that I have here, part of it, one part of it, not all of it, which ones? The ones from 25 to 21. If you say this is instruction, so the instruction 25 to 21 will connect to this first address. There's a nice figure in the book, don't worry. I mean, don't try to do this. And the second one is going to be the next bits, instruction 20 to 16, hopefully. That's great, because I have one of my operands coming out here and the other operand coming out here. Now I can take this operation, this unit that can do interesting things with it, which was the ALU. I'm just going to turn it like this way around. So I have this kind of unit, ALU. And it has 2 inputs, A and B. This is 32 bits. This is 32 bits. The result at the moment will be 32 bits. And I'm going to simply and nicely connect them together. And of course, Frank was supposed to do this yellow. Okay, there you go, ALU. This is a combinational block. And someone has to tell us what kind of operations we are doing. And we realize, I'll show you in a second in the book, there was a 3-bit function that was selecting the operations. Just a second, where did I put that? I lost it. I didn't lose it. We said this is the function. It was a 3-bit code that was telling us which operation we are doing. So the same instruction also goes to this magical control cloud, which we are going to come at the moment. So this is again the instruction. And in the control part, we will figure out which one of those ALU operations we should select. Now we have this output, and this output should go where? R-type instructions will write back to the register file. So we are taking this output, this guy, and we will bring it back, hopefully. Yeah, it doesn't matter. Zit, zit, zit. And this thing is very easy because I know that the instruction 15 to 11, yes, 11 tells us where we are going to write things to. That looks ridiculously simple. I have just the instruction memory, the register file, the ALU. The program counter points to an address. From there, I get the instruction. I look at the instruction. I have to figure out, we will see what happens when it's not R-type. But assuming that every instruction is R-type, what happens is the bits 25 to 21 tell us which is the first register to pick. I apply the address. I get the content of that register. The same way, this is the second register, the second operand. I apply the address immediately. At the same time as I apply the other one. In parallel, I get the second operand. Those two operands go into the ALU. Something tells the ALU what to do. Where do I know what to do? Well, there is this instruction, contains additional bits. In our case, these are the 6 bits at the very end. And they tell us, hey, if you want to realize this thing, you need to configure the ALU for doing this operation. The result comes out here, and then it will go back, and it will be written into this memory. Now, we have to also know that we are writing something into this memory. So we have another signal that says, hey, you know what? This address and this data should be written at this instant into the memory. Where's my... So I have another control signal that comes down, and let me just not say a random number here. Reg write. Okay. Now, if you now end up coming to the control part, what happens is we end up looking at a number of things that we are receiving from the upper part. So this is where I'm trying to explain what we are doing. Let me take my cheat sheet so I stay consistent. So for what? An R-type, we have to see what the operation is. And so these are the 6 bits of operation which I pick as the first things. And if they are 0, 0, 0, 0, 0, 0, I know that I'm doing an R-type. And then there are some numbers that I want to set. Well, there is the reg write. This one. And this should be 1 whenever I'm doing an R-type operation. And then at some point, I have my ALU operation. Now, the ALU operation could depend on what the function is in my instruction, right? So I could do addition, I could do subtraction, I could do many different things. So one of those operations will be picked up from the function bits. So the function tells us what to do. At the moment, I don't have that much more control signals, but as we try to implement more and more instructions, we will fill this thing and we will have a bunch of different control signals. And my very, very dear multiplexers will start in filling this drawing. Yes, sorry.
Why do you have 6 bits for the function, but only 3 going to the R?
That's a very good question. First of all, I'm showing a very simplified version of this thing. The ALU that we had in the lecture had only 3 control bits. I'm going to show it in the second part. We are going to look into it. Just assume that a number of functions can be realized by the same ALU operations. They are not necessarily always that distinct. and you could have a better ALU that implements more of the functionality. What we are showing as an example in the book, it's the same example in the book, by the way, is only a subset of all the MIPS risk instructions. We are showing you a minimal subset with which you can see how this thing goes. As you implement more and more, this ALU will become more complex. This thing will have more bits, and maybe there will be some additional control signals coming in. But at the moment, with this little, we will be able to do 90% of the job. There was another? Okay. Great. Oh, not great.
There are more registered instructions, R-type instructions that don't use the ALU, like jump register.
I'm not very sure. I think jump register is still I-type, but I'm not so sure. Could be. I mean, it's not necessarily that you use it. No operation, after all, is also an operation. So there will be things that end up doing nothing. You know, you can also select the address 1 as 0, address 2 as 0, and you know that register 0 is 0. So 0, 0, do something, will not generate you something as well. I mean, don't worry, it will get more worse. But there is I mean, it's really in the slides, hopefully. And I'm cheating and looking at here so that I use the same names and same drawing as in the slides. Otherwise, I get lost. So, but great, keep it coming. Other questions? Let us do something more. Let us, before the break, try to manage another type of operation, because at the moment, we can just do things with this instruction, with the register file. The first thing that we would want to do, probably, oh, by the way, sorry, let's do this once again. Read one instruction. Program counter shows it. Instruction, we decode it, we understand what it does. Pick two operands from the register file, work on them, calculate the result, write it back. That's one cycle. So program counter, clock starts. Clock comes. So that's one cycle that we have to finish, all in one clock cycle. This is why we call it a single cycle architecture. And regardless of what the operation is, hopefully that the ALU will be able to decode all the, 64 different R-type operations. We are actually good. But now let's do something evil. We want to bring some data into our register file. We want to load a word. Now comes the question, how do I do a load word type of thing? And we know that these are more or less the same, but we have some issues here. So first of all, this thing is no longer all zeros. Let me cheat. Load word happens to be 100011. I didn't choose these, don't be upset with me. And then here I have an immediate value. Now, just so that we remember, how did this instruction look like? If we had one example for load word, it said something like load S0, and then there was a constant, some constant, let's say 42, 40, and the register was something like T1. So I needed two registers and one immediate. So one of the registers is here, the other one is here. But unlike this, I need to do something quite different. So let's also write this thing that was 100011. So this is load word. Okay. So let's see how we have to do it. What do? I take the content of this register and I add a constant to it. Now, the good thing to realize is the first register is easy. I have it here. This is the guy. From the instruction, I read the first register. It comes here. I go to the ALU. And the ALU can do the addition for me, no problem. So we can go here and, sorry, of course I have to try it 4 times to get it done. We say, hey, let's do an addition, whatever the function code is for addition, we will be good. Okay, what do I add to? Second register? No. I'm not going to add to this register because this is not going to be, the second register is not something I read from. The second register is actually, this value is where I will be writing it to. The result will go, instead of this one, will go somewhere else. Now that's annoying. So it means that I have 2 options. And 2 options usually means that I have a nice circuit structure that we call a multiplexer. I love this thing. So this was my instruction 15 to 11. And this one was my was the upper instruction. So I have to select to which address I am writing to. Hopefully I didn't make a mess. And this means that I have yet another control signal that goes down. And in this case, this guy is the rec destination. Yes. So when I'm doing an R-type instruction, I am choosing this address, 1. When I'm doing a load word, I'm choosing the other guy, this one. So the address to which I will write to will be picked up from this register. And this control signal will tell me where I'm picking it from. Hopeless? Don't worry, I'll do it twice. More. Okay. So far, so good, but I'm not adding this register, so where do I find the second value? I have 1 register, I will add the constant to it. Where do I find the constant? You say, well, Frank, the constant is already here. It's part of the instruction, but it is not quite ready. Why is it not quite ready? Well, you know, because how many bits do I have here? This much. 16 bits. How many bits do I need for the ALU? I need 32 bits. So what happens is I have to take this number and I have to extend it. And of course, this was the yellow part. So this was 16 bits that I stole from instruction 15 to 0. And I blow it up to 32 bits. And now, again, one of my favorite guys. Oh, my God, I forgot this multiplexer. Now here I have 2 options. Once again, a multiplexer comes into play. Yellow. The value that goes to as the second part of the ALU either comes from the constant, immediate, was 16 bits, gets extended to 32, so that I have a 32-bit value. And let me see, if this is 1, I pick one of them. If it is 0, it's an R-type operation. So this is the source A, this is the source B in the book. And I have yet another control signal going down to my control thing. And this one we are calling ALU source. ALU source. Give me a second. And ALU source for an R-type instruction was 0. And for let's just draw here a line so that and for a load word type of thing is 1. I will choose this input for the ALU. I will get the value from the instruction, the first 16 bits. I will blow it up to 32 bits. I will take the register address from here, get its content, add it to the immediate, and I have a value. Okay? That looks very good. And now I have a 32-bit value. What is this value? Well, this value is the address. This value is the address that will end up going to the data memory, which I'll put here. So this is the data memory. And the data memory has an address input. It has a read data, and it has a write data, and also has a write enable, as well as a clock somewhere. So now, whatever comes out of the ALU is actually the address. This is the address that I use to find the data in the memory. And what comes out of this is actually that will get written back to the address that I already discovered. Now I will do one nasty thing so that I stay consistent to the drawing, and I say, you know what, let's put this guy, instead of making it like this, I will bring it back. I say, either I take the ALU input as it is, the ALU output as it is, or I select between reading from the memory and reading from the ALU. So I have yet another multiplexer, and now I connect this one, this thing here. Okay, let me just add the correct numbers there, 0 and 1. 0 is ALU, 1 is reading from the memory. And obviously, once I have something from that, it will be another control. So this is Mem-to-Rec. And I have yet another control signal that goes into the cloud, Mem-to-Rec. And for the R type, Mem-to-Rec is 0. And for the load word, the Mem-to-Rec is 1. Now, before we go to the break, just a quick summary. And we will be writing back to the register, so the write enable will be 1. Now let's just try to take a little bit of look what we made. We now manipulated things the following way. I just had R-type instructions, and now I added the I-type, some of the I-type instructions. Specifically, I added the support for LW, load word. And load word I know because the operation code will be 100011, whatever. Once I read from the program counter the instruction, going here, the control part will realize that, hey, the operation is this, and then we'll be able to make the decisions about which multiplexer should have which value. In this case, once you see this, you will say the register destination should be 0. Register destination chooses which one of these addresses should be used to write back, is the address of the register being written back. If it's a load word, it is 0, meaning that I choose this input of the multiplexer, instruction 20 to 16, meaning this guy here will be the destination. I will load the data into here. Going forward, okay, you realize that I'll be writing back to the register file because load word will load something into the register file. I know that the ALU is going to use always the first register as one of the operands, but the second one doesn't come from the register file. Instead, is part of the instruction, And while decoding it, I realized these 16 bits, I extend it so that it generates me a full 32-bit address. That's a very simple operation, right? I just copy the first sign bit. I select the correct input. The ALU generates me an address. And instead of writing the address back, what I do is I go to the memory. I present the address. The address I'm presenting now is the content of T1, which was here, my immediate, both of them added, gave me the address. I present the address here, 32-bit value. I get back the data from the memory. And now I know that I should be picking this, not the content, not the output of the ALU, and I write it back, write enable, to the register file. I know it's a lot. We will repeat this a few times, and we'll add a few more instructions. And hopefully, in a couple of repetitions, this will not look as crazy as it sounds. So now it's a very good time to take a break, and let's continue at 20 past. Sorry. You're back. After I've explained the exam questions, now let's continue with the... So, the program counter. What happens to the program counter? Well, the program counter normally will end up getting incremented every cycle by an adder. And it's actually very simple what happens to it. It will get incremented by 4. Why? Because every element of that this instruction memory is byte addressable again. So the next instruction will be an address of 4 away from the previous one. So we just add to it, and there we have the next program counter, as simple as that. Now, there were a couple of people asking, and it's a very good question, Frank, you draw this thing, how does this relate to there? So there are a couple of different paths. So the first one is program counter, present state, you add 4, and then you come back, and that's the next state. So in this case, we start from the program counter, we add 4, we go to the program counter again, which is not a very difficult operation, right? I mean, compared to all the other things I'm doing. Then we start from the program counter, pick things, supply the address to the instruction memory, read out the 32-bit value, take a look at what the 32-bit means. Specifically, the first 6 bits tell us a lot. And in this case, if, for example, they were 10011, we know that we have to select here 0. This is one address. I pick one address here. I read something out. That one gives me a value. The rest of the value I pick from the instruction. I extend it. I add them together. My God, gives me an address. I read this thing out. I have this, and I come back and write back to this register. This point will end up being here. So program counter, memory read, register read, ALU, multiplexer, memory read, multiplexer, back to memory. Sorry, there was a question. Somewhere? Yes.
So why don't we change up the order of the registers in the archive?
That's a very good question. I mean, I'll just repeat. So I could say one of those multiplexers if this guy and this guy would have swapped. Now, this was the decision of the architecture. So this was a decision being made by the computer architects who were devising MIPS. And they were making certain compromises. They were sitting around the table. Let's say they didn't care about this multiplexer so much. Various reasons, you know, we could be more critical of them, we could be more understanding of them. Maybe a couple of other instructions will show us that this was a better choice because something else was happening. Maybe they just overlooked it. But that's a very good question in the sense that the architecture just tells us how to build it. And once you agree on the architecture, the job of microarchitecture is just implementing it as best as we can. We are no longer, well, you could have argued that part of the architecture design phase is sitting around, trying it out, seeing whether or not it's efficient and things like that. And you would assume that they did this, and they ended up saying, you know what, I like multiplexers. Let's put an effort to put one more in there. Could have been. Other? As I said, don't worry, we will go over this on the slides because we have the exact same information also on the slides, and we'll come back to it. Now I want to add another instruction because we did a lot of nice things, but we didn't do yet. I mean, we can do a lot of R-type operations, and R-type operations only work on the register file. We can bring new data into the register file now that we have the load word. But we also want to have a store word so we can write from the register file back to the memory. So how about we talk about what we do for the store word. And let's just quickly say, hey, store word is very similar. But it works a little bit differently, right? In this case, it's the content of this register that gets written into this address. So the address calculation is exactly the same, but instead of using this as a destination register where we are writing, it is actually this value that will end up getting written into the value there. Now I have to make sure that I don't make a mistake here. Yes, excellent. Now, store word. Does anybody know by heart what the opcode is? We won't ask these as an exam question. You will actually get these delivered. Don't worry about it. So it's 1011. Okay. Now, the first thing to realize, or the easiest ones to realize, is the following. Am I going to write back something to the register file? Store word. Who says no? In the store word, we are not writing anything back to the register file. So we are not going to write anything. Therefore, it doesn't really matter what I have for the register destination. I'm not writing anyway. Who cares where I get this address from, okay? Does that make sense? Also this side? Side is good? Okay, so there is a, also so that you don't fall into the trap, R-type instructions all are exactly the same, whereas I-type, J-type, they are individual. So load word and store word are both I-type instructions, but they do quite a bit different things. The only similarity between them is they both have an immediate and they have two registers. So I-type is not necessarily this thing, so there could be many different instructions that have the same type of opcode. There is actually quite a bunch of them. Now, but the memory calculation, we still need to calculate the memory address, right? Because we want to write to a location in the memory. So that part will stay the same. How do I do it? Well, I take this register, the content of this register, I add the immediate value. So that part of the calculation should still be here. The ALU should choose the immediate part, extend it, that will be the 32 bits. I have my register here, the one that was supplying me the base address. I edit them together, and I have my address. But now I'm not reading anything. I'm writing something. Where do I find the data to write? Which one? It will be this guy. It's the content of the second register. Now we'll go and we'll get written into the data memory. And how do I write that I am writing into the memory? Well, guess what? There's going to be another control signal. And this, we were never writing to the memory before. So in R-type instructions, we didn't write. We definitely didn't write. Here we didn't write. But here, now we are going to write. The ALU operation is the same operation as before. We are still adding the immediate to the constant. And mem to rec, what do you say about that? We don't read back anything. So I don't care if we read back the ALU or this. It could be anything that they choose, because we are not reading from the memory. If we are not reading from memory, it doesn't matter. We are not going to write anything back here. Just like we didn't care what the address was, it will be there. Now, important distinction is, this is not undefined. It's just that I don't care. When you write code, when you synthesize it, the synthesizer will pick something. They could pick 0, they could pick 1, whatever makes their life easier. Remember at the beginning, when we are doing combinational logic, optimizations, and things like that, we said, hey, we can take advantage of the don't cares to make our life easier. So this is what will end up happening there. Is that? No, not. So there was a question. How does it look like? Yes? No. Question? No. It's okay. I mean, looking at you, I think like it's like 50%-ish okay. Who says more than 50 okay? Okay. Okay. Who says 10% okay? Okay. Don't worry. I'll ask it once again. Now, there are other type of very important things because we realize that we are not manipulating this program counter at all. You know, we are just staying where we are. Now, why don't we try to make something that is a bit more exciting? The talk is, about one instruction that we really have to have is a branch. We don't have to have all of them, but we need a branch. And let's try to do a branch if equal to. By the way, the branch not equal to will be very similar. For that, we have an opcode, if I don't lose my cheat sheet. And it seems like the opcode is 0, 0, 0, 1, 0, 0. Don't you think that this being an architect is great? You come up with like random stuff, and then you let the microarchitecture people like slave over it. Like there was this guy and saying like, guys, what shall we call branch if equal to? What shall be the code? And it says like, okay, who says 0, 0, 0, 1, 0, 0? I say, yeah, that's what I feel like. No? Yeah, there must be a typo here. Okay. Now, branch if equal to is a funny instruction, right? So the BEQ has two registers, S0, T1, and then has an immediate, a label, let's say, whatever, label something. And we knew that this label will get translated to a location, to an address, which is within, will end up being an immediate. What will it mean? Normally we are here at the program counter, so this is where the branch equal to instruction will be. The next instruction will be whatever the program counter is plus 4, and this thing will be an offset to it. We will say jump 10 addresses ahead, jump 5 instructions behind. The assembler, if you remember from last week or 2 weeks ago, the assembler will take your humanly written labels, where you say go to loop or whatever, end loop, whatever, will then look at the assembly and will realize how many instructions you are jumping ahead or behind. And for that, it will create an immediate, a constant value. Now, this constant value will be added to the program counter. Let me actually, give me a second. Yeah. Let's do this. It's not a smart idea, I know. Okay, let's just briefly go back to this thing. No, wrong? What?
That's it. Okay, maybe it's sensitive. I was going to ask if the offset is added up to the 4 that the program counter is.
Yes, it will come. So in the appendix of the book, you can look at every instruction, and this is the appendix has actually the description of what is going to happen, and this was described in the instruction set architecture. So the moment people sat down in a committee and decided how the instructions should look like, they made these decisions. So you read and say, hey, the opcode is 00100. And what will happen? If RS equals to RT, so if these two registers are the same, then the program counter should be the BTA. BTA stands for branch target address, and it is program counter plus 4, which we already have. So this was PC next, so this is PC plus 4. On top of that, we should add the signed immediate, so this value, And not only that, but we realize that this is going to point to a word address. So there is no point in, having 0, 0 at the end. So we shift it also by 4. So it's a multiple of 4. Essentially, the immediate shows you how many words ahead or behind, and then we convert it to byte address. So we say, the next address would have been PC plus 4. Okay. Now let's add this immediate on top of it and shift it by 2. This comes from the description. And we also need something else. We need an ALU to make sure that we can compare these two. And what we will do is we will subtract RS from RT. So we are going to use the ALU. We are going to trick the ALU into saying, subtract these two numbers. And we are only caring about it so that we can find a 0 flag that the ALU somehow integrated into it while he's doing all these operations can tell us if the result is 0. Finding whether or not two vectors are equal to each other was one of the first exercises you did already in the class, so you realize it's not a very, very difficult operation. We could squeeze that functionality in here, and we are going to do that. And the problem is, sorry, go away. We need a second adder. It's kind of annoying, but we have this giant ALU here, but we need a second adder because while we are subtracting this, we are in the same cycle, right? I cannot reuse the same thing to do two things in sequence. So I will need a second parallel adder to calculate this thing. Now, let's go back to, and then, of course, the program counter will have two options. It will be either the one that we calculated, PC plus 4, or the new branch target address. Now let's just do this once again on the board. This goes away. Room has help light blackboard. We come here. We realize what we will have to do. Okay. So let's get started. And these are my control signals. Now I know that I have a, it's getting a bit trickier. Okay, first of all, let's agree on some simple things. I don't need to have a register destination choice. I mean, I'm not going to do, I don't care. I'm not writing anything back to the register file, right? I'm not writing. We already agreed on this. And I'm also not writing to the memory. I don't care anything what happens to writing to the memory and things like that. But now I actually care about the ALU operation. What I want to do is I want to run a subtract operation so that out of the subtract operation, the resulting number, I can detect whether or not it's a 0. And the ALU source now, interestingly enough, can no longer be this thing because I'm going to use these two registers as the source 1 and source 2. So I'm going to subtract these two from each other. And now you see that I'm not keeping them the same. There was a question coming up. Now I am selecting actually 0, this register output, as my second operand here. So this one is going to be 0. Now, of course, this is not only enough. We will have to do some more tricks. And the first trick that we are going to do is I actually had my lovely sign extended version of the constant. So I had this immediate. The immediate was there. You know, it's almost there. I know what PC plus 4 is. I also have it here. And now I just have to add this thing. First of all, let's shift this to left by 2. Let's do this. And now we have the problem that I need to add this number. Oh my God, where do I do this? To an adder here. And then I take this result, now gets really horrible. And I take this guy all the way back, and I come back. And now I have two choices for the next state of the program counter. It's either PC plus 4, or we have another multiplexer here. And this one selects, let me see, this is PC4. PC4 is this. So this is either 0 or this is 1. And the address is called branch. Now, unfortunately, my clever way of writing did not allow me this, so I'm bringing branch here. Sorry about that. Bad design. And I know that I'm not branching here, I'm not branching here, I'm not branching here, but this is the one instruction where I am going to choose this branch address. So the next instruction will not be program counter plus 4, but it will be program counter plus 4 plus whatever was the immediate left shifted, edit, comes back and goes and becomes the next program counter. Every time you write an if or for, imagine this is happening. Okay. Questions now. How do you feel about it? Is it looking okay-ish? Okay. Now, what happens is we have actually similar thing here. At the top, we have a data path. From some of these things are state holding. This one holds state. The register file holds state on the right port. The data memory holds state on the right port. And we have several paths that we can go through. Data flows more or less from left to right, the way that I've drawn. And then there are all these different control signals that select whether or not I'm taking this input or this input, whether or not this address is this one or this one, whether or not the ALU chooses this register or the immediate, whether or not I read directly the output of the ALU or I read from the memory. I make these type of decisions. And what happens in this control path is actually quite simple. You take a look at the opcode. The moment you look at the opcode 101101, you know what you should be assigning to each one of these control signals in the same cycle. So the moment the instruction is available, you know what this is. You also already directly know how you should be controlling each and every individual control signal to configure the data path to do what you want. Sorry, yes. Oh, sorry. You're very good. Sorry. You are excellent point. Frank loses some points. We have a 0 flag here that also goes back to the cloud as one of the decision-making things. You're absolutely right. There is a couple of other smaller things that happen, but the gist of it is this. Now, what the R-type instructions do, you will realize that only depends on whatever is in the ALU, because this function is being, let's say, transmitted to the ALU. And the more capable the ALU, the more R-type functions I can realize. I have, at the moment, 3 different instructions, I-type instructions. I didn't do the J-type yet. We will do it tomorrow. But you see how this would go. The moment you have an instruction, you can open the back of the book, the Appendix B, take a look at the instructions, and you'll realize, okay, I mean, there's not that much magic happening. Now, there are these discussions we will have, whether or not, what would have to happen if I add more instructions here? Do I need a few control signals? You know, branch not equal to, right? You have similar kind of things, and this and this, and you realize this will be some sort of case op. Branch equals to this, rec this equals to this, rec write equals to this kind of writing. Now let's jump back to the slides. We will do this twice. So tomorrow I'm going to do this again, but with different parts of the slides. Let's hide this. Not completely hide it. Okay, it can stay like this. Okay. Okay, so now this is the first part of the slides. This is meant to accompany this lecture. Tomorrow we will make another tour through it using another part of the slides, okay? So let us start with the building blocks. Room light. Okay, this part we already discussed. Here, at some point, we wrote our assembly. The assembly was translated into machine code, magically landed inside the instruction memory. And here, the program counter, whenever you press reset, ends up pointing to a very specific address, which was agreed by the MIPS community in 00400000, whatever. And when you go there, you find this value 8C0A0020. And when you decode it, you realize that this thing is load word from base address 0, go 32 additional addresses, find whatever there is, and write into the register T2. So this is apparently what it says. Now, let's just try to take a look at how we are implementing these things. So the first thing we have this instruction memory. So this is this part. And we need to find a program counter that goes with it. So this is it, actually. We have a program counter, rec type. We have the present state, the next state. And actually, what happens is, if we are not doing anything fancy here, the next state is the present state plus 4. This is before we added all these fancy things. Once we start getting fancy, we will probably write more things in here. But at the basis of it, when there is a clock coming, well, if there is a reset, this is the default value. And if there is a clock coming, the next state will become the present state. That's it. That's my program counter. Nothing fancier than this. Yes? Why not? We covered this, actually. It's historical reasons. There's a very long and boring story about it. Historically, ASIC designers ended up using active 0 resets. FPGA was a young child, so it came out in like end of 80s, and they asked exactly the same question you said. Why negative? We will be positive. So most FPGA designs by default use, and they had to make this difference. So the code that runs on FPGA and the code that runs on ASIC usually ends up being slightly different. There's no real, these days, back in 1970s, there was a reason. These days, it's a historical baggage. My grandfather was doing it that way, and I will fight to my last breath that I do something like that. You're completely right. Okay. So the moment we have the program counter, the moment the program counter gives us something, I already know where to pick the data. So I have the program counter, I can pick the data, and now I have I have an instruction, A. And I know that I have 3 different types. We just saw 2 of them until now. And the R types use 3 registers, the I type, the one with immediate values, and then there's a J type that we conveniently always not talk about. Isn't that great? Red flags, they will ask it in the exam, kind of thing. Okay, so what we will cover in these slides is only a small subset, and or add, sub, set less than, load word, store word, branch if equal to. Notice that we have already covered like these things, sort of. These we covered. We didn't we didn't add this add immediate and J yet. And maybe some of those we didn't really mention, but it shouldn't be so difficult. Now, I have 3 register operands. 2 of them are source. 1 of them is the destination. We already know this part of the story. And we already know that once I have these things, the machine code, we can directly map them, and each part tells us what to do. This one is one of the source registers. This is one of the source registers. This is a destination. I will write it back to here. I'm not doing any shifting at the moment. Who knows what this is about? And then this is the function. Apparently, if this is 32, I'm adding. If this is 34, I'm subtracting. Okay. We also discussed that R-type operates on a register file, and we wrote it here. And a lot of you asked the question, you're absolutely right. How come I have a memory that has 3 addresses, 2 of which we read from, and 1 of them we write to? It seems like cheat code. You know, like the memories were like these boring structures where you supplied 1 address and it took forever and you read something out. And just to show you that what this would correspond to in very low code, it looks like this. So the entire thing is you have 32 registers, each one of them 32 bits. And I have 2 addresses. So this address from this array picks me 1 output. This address from this array picks me another output. Notice this is combinational in this code. The moment there is an address, there is an output. Okay? The only thing that is not combinational, this part, is what happens when I want to write into the array. And I only write into the array if there is this write enable. And if the write enable is used, the 3rd address into the location of the array from the 3rd address, I write whatever the input is. So this one writes the RD, these 2 read the RS. That's it. Well, sort of, kind of. You know, this is always what I do. I tell this is it, and then we make life complicated. Remember, we said that register number 0 is always 0. Remember? Okay, how do we deal with it? Well, we modify it a bit. If the register is 0, return 0, otherwise return whatever is in the array. I don't trust the programmer not to overwrite the address 0. That was one of the questions, I believe, when we were talking about the architecture. What if someone writes into it? Well, you put a hardware there and saying, no matter what you do, try reading from address 0, you are going to get back 0. Ah, sorry. Sorry?
Of the R array, the index 0 is never...
It doesn't have to be, because you see, this is a trick. This is a cool trick. I check if the address equals to all zeros. If it is equal to all zeros, I pick from the array. Otherwise, I directly return 0. I don't even look at the register array. I say, hey, the address is 0, you get 0. I don't care what's written in the array. Hopefully, now, the interesting question that you could ask, and it's a very fair question, why do I not have an array of 31 instead of 32? The idea behind compilers and optimizations is that hopefully the compiler will realize that one element of the array is never being read and never being written to. So he just says, okay, if you never read this thing, it's there, nobody knows it, let me remove it, nobody will realize. And optimization things, optimization routines in synthesizers, modern logic synthesizers, will be able to take advantage of that. You don't necessarily have to overcomplicate your life and write code that is less readable. So it's much more preferable that the code remains more accessible and the optimizations are done by compilers rather than you taking things into your own hand. Once you realize that the compiler is not doing well, then you say, you idiot, let me write you in a way that even you will understand, you know? But give the guy a chance. Maybe it will do the right thing. No? Okay. Notice that we've seen this slide before. I'm reusing it. This was at the end of when we were talking about combinational logic circuits. And we said, hey, there could be 2 inputs, each 32 bits or n bits, and 1 32-bit output. And I could define, and this is my job, I can make whatever functions I want. And I say, if the function is 0, 0, let the output be A and B, A or B, A plus B. This one I'm not using. This is A and not B, A or not B, A minus B, SLT, whatever, whatever. And if you remember, who does? Okay. If you remember, we ended up with something like this. Notice the gorgeous multiplexer at the very end. And then you say it's either an AND, either an OR. Maybe I will invert the B input, so I have the inverted B, this. The inversion trick also helps me with the addition versus subtraction. We were talking about this. And then I had this funny set less than function, which was buried in there. It's not very important at this moment to understand what the ALU or how the ALU went. We can go back to that part of the slides. The important part to realize is we can build a combinational function and define a number of operations and make it configurable so that based on the control input, which is this guy coming in here, given these inputs, I can manipulate them in a variety of ways. Now, people like me spend countless hours trying to make this a bit more efficient, a bit faster, a bit more potent and things like that. That's still, a long story. Doesn't matter how we do it, we can come up with these things. Convincing? Okay. So we have most of the components for the MIPS. We did not have data memory yet. We can implement all R-type instructions, but not much else. No memory access, no immediate values, no conditional branches, no absolute jumps. Well, that's not true. We saw what the data memory will look like. So here's the data memory. And in this case, I have a large array, each 32 bits. And the output, this output, is just the same as before. Well, if I have an address, the data output corresponds to that element of the array. That's it. If you want to write something, well, we have to check if we have write enable. If there is write enable, the data input that comes into the memory will be written to the same address. I have one address. I either read from that address or I write to that address. Unlike here, where I have 3 different addresses, 2 for reading, 1 for writing. The, let's say, code of it is relatively simple. Now, this part just explains what we were doing. We want to generate the addresses. So the load word instruction to read from the memory, we need to calculate the address from an immediate value and the register. This was what we were discussing before. And we already have an ALU that can do additions. Why don't we reuse this thing? So this is what we are doing. We are manipulating we are manipulating the ALU to be able to generate the address for the memory access. What we need to do is we need to manipulate the input here. We have to sign extend the immediate so that we can add these 2 things together. And well, that's more or less it. If you want to write, we are going to need the same address generation scheme, but this time, instead of sending the data back, it is this second register that provides us with the data that we are writing into. Now, there are several options in the data path. These are all these things that were going down. So the ALU input could be this or that. The write address of the register file could be separate. Write data in could be separate. Write enable of memory, etc., etc. And all these, we said, define some muxes, and these options are our control signals. So this is a good point to stop. Tomorrow, we are going to go through them again to strengthen this thing, and then we will add the missing instructions, jump, and add immediate, which will make it a bit more complex, and then we will talk about the performance. And next week, we will make it even better. Thanks a lot.